Assalamualaikum and hi! So in this video, we will talk about new separation process and their potential. And this is our team, and we are consist of 4 members. And for introduction part, we will talk about importance of separation in our industry, such as oil and gas industry, pharmaceutical, food processing, and also wastewater treatment. This process allows for the purification, recovery, and refinement of valuable materials, ensuring the product quality, process efficiency, and also environmental compliance. So, the objective of this video is to introduce and discuss new separation methods that offer improvement over traditional method, and we will explore the challenge faced with conventional method, and we will highlight the potential benefits of innovative approach. For an overview, this separation method involves advanced techniques or technologies that aim to improve efficiency, energy consumption, and also sustainability when separating components in a mixture. This method often incorporates modern advancements like membrane technology, adsorption, or hybrid systems that address limitations of older processes that offer improvement over traditional techniques. As I mentioned earlier, these are the reasons why we need the new separation process. First, we can improve energy efficiency as it will reduce the operational cost and also energy use. Second, for sustainability purpose, it will minimizing the environmental impact and also the waste. And also, this separation process ensure the high purity and selectivity. So this will achieve the better separation of complex mixture. And fourth, cost effectiveness, as it will lower the overall process cost with innovative technology.
New separation process have revolutionized industry by providing more efficient, precise, and sustainable solution to address the limitation of traditional method. In this section, 3 key new separation technology will be discussed, which are the membrane separation, supercritical fluid extraction, and cryogenic separation. First is the membrane separation. This process uses a semi-permeable barrier called a membrane to separate components based on their size, solubility, or charge. Here are 4 main types of membrane process, which are microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Each type is designed for specific application based on their process. The separation mechanism here depends on the principle like the solution diffusion model, where the solute dissolves in the membrane material and diffuse through, or the sieving mechanism where the membrane acts as a filter to block the larger particle. For charged membrane, electrostatic interaction helps separate ion effectively, making this technology ideal for water distillation, gas separation, and wastewater treatment. Next is a supercritical fluid extraction, which is called as SFE. This process uses fluid in the supercritical stage, which above their critical temperature and pressure. The most common supercritical fluid used is the carbon dioxide, due to its moderate critical point of 31.1 degrees Celsius and 73.8 bar, where they exhibit unique property of both gases and liquid. At supercritical condition, carbon dioxide becomes an excellent solution. By adjusting the pressure and temperature, its solvent power can be finely tuned to extract specific compound. Other than that, small amount of polar co-solvent such as ethanol can be added to the target polar compound, can enhancing the extraction efficiency. The entire process is environmental friendly as CO2 is non-toxic, reusable, and left no harmful residue. Finally, is a cryogenic separation. This method involves cooling gas to extremely low temperature, which often below negative 150 degrees Celsius, to liquefy and separate the components based on their boiling point. For instance, air is separated into the nitrogen, oxygen, and argon by cooling it until each component condenses at its unique boiling point. The process starts with compressing, where the gas mixture is pressurized. Then it's cooled using the heat exchanger and the refrigeration cycle. Leveraging the Joule-Thomson effect, where the gas cools as they expand through the cooling valve, or liquefy the component as separate in the cryogenic distillation column.
So next, we move to application and industrial potential. Let's consider the new application in emerging separation of technologies. First, we're going to go to membrane separation. So water purification. Water purification with better membrane lead to better separation, high purity of oxygen, where by using the inorganic membrane will increase the efficiency of separation. What it does is uses a semi-permeable membrane to remove impurities from water. And the process is included the reverse osmosis, and ultrafilter, filter bacteria and virus, and nanofilter. And also, it has energy efficiency, scalable, and produce high quality of water. And it also minimal the chemical use. The challenge for this for future is the membrane volume and replacement cost for membrane and pre-treatment often is required. So next, we move to supercritical fluid extraction (SFD). We have three types in industry that use the supercritical fluid extraction: decaffeination, pharmaceutical industry, and food industry. So how does it work in decaffeination? The coffee bean leaf up the steam to open up, and supercritical CO2 will flow through them, dissolving the caffeine while leaving the flavor component. The caffeine is separated and removed, and the CO2 is reused. So next, we move to pharmaceutical industry. In the pharmaceutical industry, it removes the impurities to obtain the high purity of API. In example, purified steroid, vitamin, and essential. The reason why we use this method because it's selectively safe and eco-friendly, and it's also good at low temperature. So we move to food industry. So extracting flavor, oil, and color in food industry, and removing fat or extracting mineral. Why we use this method in food industry? Because it's safe, chemical-free, eco-friendly, and preserve flavor and mineral. So next, we move to cryogenic separation. We have two types in industry: aspiration and production of natural gas. So what it does in aspiration is separate air into oxygen, nitrogen, and argon by cooling air to cryogenic temperature. The production of oxygen is used to steam making, healthcare, and water treatment. The reason why we use this method because it produces the high purity gas like in large scale and reliable production. And the challenge that we face to sustain it is high energy cost and require compliance equipment. So next we move to production of natural gas. So in natural production of gas, so what it does is separate the component of natural gas, in example methane, ethane, and propane by cooling to cryogenic temperature. The methane is used as fuel and feedstock for chemical. Ethane and propane are feedstock for plastic and petrochemical. Why we use this method? Because it's efficient for large-scale separation and produce a high purity of component. The challenge that we face to sustain this is high energy demand during the process and require a specialized infrastructure.
As for the future prospect, three key areas appear promising: AI and machine learning, energy efficient technology, and sustainable approach. AI and machine learning are transforming separation processes by analyzing data to optimize efficiency, precision, and control. These technologies predict optimal conditions, identify hidden patterns, and reduce energy use and waste, promoting sustainability. As industries focus on resource management, AI-driven innovations offer smarter, faster, and more cost-effective solutions for a sustainable future. Hybrid separation processes combine distillation for bulk separation and membrane technology for fine-tuning, significantly reduce energy demand. Integrating renewable energy sources like solar and wind further enhances sustainability by minimizing fossil fuel reliance and carbon emissions. The result is an efficient, eco-friendly system that delivers high-purity products benefiting both industries and the planet. The circular economy focuses on resource recovery, recycling, and minimizing waste through continuous material reuse. Separation processes such as depolymerization play a key role by breaking down polymers into reusable monomers, enabling efficient material recovery and reducing environmental impact. This sustainable technology not only supports the reuse of valuable resources but also enhances recycling efficiency. As industries increasingly prioritize sustainability, depolymerization stands out as a vital tool for advancing eco-friendly and closed-loop production systems. In conclusion, emerging separation technologies like membrane separation, supercritical fluid extraction, and cryogenic separation are overcoming the limitations of traditional methods. These innovations offer greater efficiency and broader applications in water purification, food processing, and pharmaceutical. With AI and machine learning integration, future processes will become even more energy efficient and sustainable, supporting global environmental and resource conservation goals. That's all from us, Group 9. Thank you for watching.